At the technical forum at the group exhibit Hydrogen Fuel Cells and Batteries. We are here at the Hanover Fair 2016. Our partner country this year are the United States of America. After a short lunch break, we are back here, and I'll introduce to you the next topic, which is a simulation-based design of fuel cell and battery materials. And for that, we'll hear a representative of Math2Market. Please welcome with me on stage COO Dr. Jürgen Becker. Big hands, please.
Yeah, thank you for the introduction. So the first thing that you would ask yourself when you hear this introduction is, well, who is Math2Market GmbH? So, because you probably have never heard of us before. So we are a relatively new company. We were founded 5 years ago. We are a spin-off from the Fraunhofer Institute of Industrial Mathematics in Kaiserslautern. And we now currently have, after 5 years of operation, around 20 employees altogether. And our product is the Geodict software. So we do sell the software, we do consulting and customization. And yeah, so the next question you will ask is, what is the Geodict software? So Geodict is a virtual material laboratory. So it allows you to do computer-aided material engineering by providing material models and prediction of the material properties. So with the software, you can import CT scans into the computer. You can create 3D models of microstructures. You can then analyze those structures, and you can compute physical properties like flow, like diffusion, like particle transport, or stiffness of the material. So this can be used in a number of applications where, for this forum, the most important is the electrochemistry for fuel cell and battery materials. But of course, you can also apply that to all materials where the microstructure is really important for the behavior of the material. So, as you see here in a few examples, we can apply that to cathode materials, to lithium-ion batteries. We can apply that to gas diffusion layers of PEM fuel cells. It can also be used to model carbon composites, metal wire meshes, but even natural materials like sandstone can be simulated and analyzed. So in a PEM fuel cell, which are the materials where we can use our simulation tools on? So you can see here the well-known sketch of the fuel cell that you will maybe all be familiar with. So on the left-hand side, the hydrogen comes in, and then in the center you see the membrane, and on the right-hand side there's the oxygen channel, where then the oxygen recombines with the hydrogen to form water. So on this anode side, there's usually a gas diffusion layer which is made of fibers which have a diameter of 7 microns. We have pores in between those fibers that are around 30 microns, and the thickness is around 200, or nowadays maybe even lower. And well, this is a porous structure on this side, and if we look more closer to the catalyst layer, we will have a microporous layer with carbon agglomerates and pore sizes of just a few hundred nanometers. And there's a they both form a sandwich, the gas diffusion layer and the microporous layer, where the microporous layer penetrates in the gas diffusion layer and forms cracks. So there's also a little bit of microstructure involved. And there's a catalyst layer that is also composed of carbon agglomerates, of ionomer of platinum particles, and where we also have small pore sizes. So what are the functions of those materials? So we have pores, and the pores, they should provide the oxygen transport, and also they are responsible for the water removal. On the other hand, there are solid in this materials, and the solid has the function, it has to provide the conductivity, it has to distribute the heat in the material, and it has to provide stability. So where for this, we need, for the transport, we would like to have very big pores. Ideally, everything's open, but of course, for the mechanical stability, we would like to have no pores at all. So there's kind of an optimization that needs to be done for all of the materials to have the right size of pores and the right stability and conductivity. So with computer-aided material engineering, you can now perform the following 4 steps. So step 1, you can get the material into the computer. So with that, you usually can do a CT scan, which nowadays allows resolution down to half a micron, and which results then in a 3D image with about up to 2,000 cubed grid cells that you get out of the CT scanner. And so this size of grid cells then requires some specialized treatment in the numerics, because we are talking about 8 billion or something unknowns that you would have in your equations that you solve probably on there. The second step is then you can analyze those structures that you have imported from CT scan. So you can compute the pore size distribution, the percolation paths, fiber diameters. You can also compute physical properties like flow, diffusion, or mechanical stability. So now you can just import something, you can analyze it in a computer. So that's halfway done when you want to do material engineering. So the third step is you have to create your own models now. So you want to prescribe some parameters for your materials. For example, for a gas diffusion layer, you want to say, I have a certain porosity, I want to be able to change fiber diameters, the fiber length, maybe also the orientation that the fibers have in average, and these kind of things. And then you can let the software generate such a structure. So this is a model, not a CT scan that we can see here. And then, of course, you can do the same analysis also on the model, and then you can analyze models, the real material, and you can compare where you could do improvements of the material or not. So I'll show a few project examples that we have done in the last years with some different partners. So the first thing is here, we can compute how a gas diffusion layer would look under compression. I mean, usually you compress it, of course, under the ribs. The diffusion layer, if you take a CT scan in ex situ, it looks quite different than when you build it into the fuel cell where you have it compressed. So you can compute how the fibers look like when you compress it step by step to different compression levels, and that then can analyze what the properties of such a media would be under compression. Yeah. You can also model, by analyzing the pores, how water would enter into the gas diffusion layer when you have it entering from one of the sides. And you can now consider some modifications. For example, here in some rather academic example, we tried what would happen if you have some patterned wettability in the gas diffusion layer. So we have an area in the center here, which is marked in gray, where we have a higher wettability. And then we can compare at a certain capillary pressure what is the availability of water pass through the material. So we can see then that for such a material, for example, we'd have some better permeability for both water and air when we have patterned pathways. So another example here is a FIPSEM tomography of a battery that was imported into the software. And then we can use this image to run some computations on it. So, for example, one can compute on any structure kind of a pressure-driven flow through the material, if we have that, or let the video run. So, or on the next slide, what is more relevant for batteries, you can also see and compute the diffusive flux through the pore and the binder that we have there for ions or for other, also for diffusion of electrons, for example. So, but this is not also only relevant, of course, for electrochemical materials. You can also use that for very different kind of topics. For example, it was used to model paper dewatering fails, ceramics, a desalination membrane from our various customers. And you can also use this for carbon composites to model the stress strain curves under some cyclic loading, where here on the picture you can see where some cracks and damage appears when you do a tensile test and compression of a carbon composite. And last example is a very different field. You can also use it to analyze the flows through rocks, so which is used in the oil and gas industry, for example, where you can analyze if you take a core sample out of the earth, and well, if you take it out and do an experiment on that, you have the problem that the rock is not the same status when it's down 1 kilometer in the earth. So in the simulation, you can apply a geostatic pressure on it, and then first compress it, and then look would this change the model, like here the permeability, for example. So with that, I come to the summary. With the Digital Material Laboratory GeoDict, you can import CT scans or FIB-SEM data. You can create models of 3D microstructures. You can analyze those structures geometrically, and you can compute properties of those materials. And with this, I thank you for your attention, and you can visit us at our booth at it's actually not 63, it's 62/3, and on our webpage, geodict.com. Thank you.
Thank you very much. Once again, you can visit our speaker at booth number D63. And big hands, please, for Mr. Dr. Becker. Are there any questions at this time from the audience? Then you can take all your questions to booth number D63. Once again, thank you very much. Our next talk will be at 1:40. That will be the reforming and high temperature fuel cells. And for that, we'll hear Björk Andresen, Managing Director of ZEG Power. That will be at 1:40. Okay. Ja, ging schneller durch, als wir gedacht haben.